All right, welcome everybody to the actual last day of school. Originally, this was just going to be a project day for Volley Shipperty, but I got some good questions in the 12 o'clock class, so I'm actually going to teach you something new that might help you with Volley Shipperty. In fact, it ties in with a lot of things. And so there's this article by John Carmack. It actually came out a while ago, but our Lord and Savior, John Carmack, he wrote an article about the benefits of functional programming in C++. Functional programming, your computer science professors are going to tell you is like the future of computer science. At Fresno State, they teach Haskell. And functional programming has been the future of computer science for 30 years and maybe will be for the next 30 years as well. There's a lot of neat things in functional programming. The only thing that matters is you can learn about those things, but pure functions are kind of the main takeaway. Like when I learned how to do functional programming, this was like a game changer for me. So, and this ties right in with Volley Shipperty and TDD and things like that, because a lot of people I think are going to do TDD instead of networking because they're afraid of it. So how can you TDD something like this and get, get ships or something like that? And X, Cn into X, return X. Like, how can you make a test for this code? What input do you give it? What output do you expect? How can you prove that this code is correct? What do you guys think? Guys seen this? We got a... This is how, like, a lot of code on, like, Geeks for Geeks, which is one of the worst sites ever. I think Zybooks does code like this. They write a function that has a CNN inside of it. How do you write a test for this? You know? How do I say, like, you know, if get ships not equal to 20 die? Like, how does that even, like, how can I make a test for it? What do you guys think? Seems weird, right? Like, there's no input, there's output, but the output comes from the user. So how do you test it? No answers. That is correct. There is no way of testing this code. Simply works correctly. What is correct for it? I don't know. The user is typing in a thing from the keyboard, you know? Like, how do you, you know, you can mock up a keyboard connection, I guess, you know? But, like, there's no way of saying what is correct for it, because it's different every time. It's dependent upon the global state. And so, yeah, you could probably set up some sort of, like, buffer and feed data from the buffer into it and see if the data you get out is equal to the buffer. But this is really kind of annoying, right? It's really kind of annoying. Whereas if you have a function like this, integer, I don't know, Bob, and X, and Y, whereas if I have a function like this function doesn't rely upon any external state. It doesn't require any dependencies on things outside of itself. It is like your classical numerical function in algebra, right? It takes in two parameters as input, it does some computations, and then it returns a number as output. And so I can test this. This is testable. This is something called a pure function. A pure function has no side effects. It's not writing to disk, it's not reading from the keyboard, it's not messing with your network state. You can simply pass things in, get values out, and see if they're correct. And so we could say if Bob of 0 to 100 is equal to 50/50, then cout test passed. I'm not even using the gtest suite here. I'm just else cout failed. I'm just literally just making it myself, you know. So if we compile this code, run it, you can see the test passed, right? So I put in some numbers, right? And I get a number out, and I can try this with any number of different combinations of inputs and outputs. You know, what if y is less than x? Should we handle that? What if there's negative numbers? Do you guys understand? This is a side effect is anything that like goes outside of that's why it's called a side effect, right? You've got your inputs, you got your output, but anything else, like a cout statement is a side effect, you can't test it. So do you guys see how this is testable and the previous one was not? Sad face. Yeah, no, we had people in class today, for sure. Okay. So this notion of a pure function is kind of what you. And Carmack's point here is that like not everything you do has to be pure. Like at some point you're going to be reading from disk. At some point you're going to be talking to the network, but you want your functions as pure as possible. Okay. And so some of the other benefits of pure functions is thread safety, which we're going to be talking about today, and reusability and testability, which is the thing for volley shipperty that I care about. Understandability, maintainability. Whereas when your code is constantly like reading from disk and writing and manipulating global variables and all this kind of stuff, then your code is not pure, and it can be very difficult to track down bugs with it and things like that. So basically, you don't have to go pure functional, and that's actually a takeaway. When I learned functional programming, I never wanted to write in a functional language ever again. I mean, it does a lot of cool, neat stuff, but at the end of the day, I'm somebody who wants to make a system that works. And at some point, you're going to have to read from disk. Like in a purely functional language, cout is impossible because cout is changing the state of the screen, you know, and you can't print anything. So, yeah, Haskell is taught at present state. And so I like being able to do things at the end of the day. But I'm most definitely with Carmack in this essay here, where after learning functional programming, I'm like, thank you for teaching that to me. I never want to do it again, but there's a lot of really good lessons there that I can take from it and bring into my C++ code to make it look a lot nicer. And he's really on point on this one. So let me post the link there for you guys on that and read it at your leisure. It's actually really good. So, yeah, so what I want to talk about today is actually the thread safety thing here. Okay, so a pure function with value parameters is completely thread safe. With reference or pointer parameters, even if they're const, you need to be aware of the danger that another thread could be modifying your thing. So what the hell is a thread? Okay, a thread means you can actually run a function on a different CPU. Okay, for something like this, doesn't matter if I have 10 of these going at the same time that are all running on different CPUs. Are any of them going to step on each other's toes? They each have their own copy of sum. They each have their own copy of x and y. They're doing their computations like off on their own CPUs. Is there a threat there? You know, if we wanted to have Bob, you know, parallelized, is there a threat to having Bob be parallelized? What do you guys think? Bob might get hurt. Exactly. So we can call this sum up if you want a better name of what's going on here. So we're summing up all the numbers from 0 to 100. What's the matter with this? Sum up. And so, like, yeah, it's like we can have like 10 copies of Bob all running at the same time, and they're not going to mess with each other. Whereas if I did something like this, if I made like int sum equals 0, and I made this a void function, and I did that, then, okay, I could do something like this, sum up 0 to 100, if sum equals 50-50. Like this will work, I guess. All right, I'm returning the value as a global. Should maybe hurt you a little bit to see, philosophically, to see this. But like I could do this, right? We'll still pass the test case, right? Because you guys all know the sum of 0 to 100 is 50-50, right? It's pretty common knowledge. So what happens, though, if we have like 3 sum ups running at the same time? Are they now going to step on each other's toes by writing to the global? Do you guys understand by stepping on each other's toes? Yeah. Like they're all going to be writing to the same output value. And so if you have 3 of them going at the same time, they're all outputting to the same variable, and just everything's going to break. Yeah. So this is bad, and this is a side effect now, right? Because our function is no longer pure; it's writing to a variable outside of itself. It's mutating, we call it, manipulating, changing the global state. The global state is this guy. This is a global variable. So let's not do that. Let's put this back here. Let's actually do this. Change word uint 64t next dot next dot next dot next. Okay. So just in case we have bigger values here, uint 64t sum equals 0. Okay, so now it's back to being pure again. Back to being pure again. So if sum up 0 to 100, 50, let's verify this is correct. All right, cool. All right, now we can try running this on different CPUs at the same time. That's kind of cool. You guys want to learn how to do that? A little parallel processing for the last day of the semester? Let's go. So Thread is a library that allows you to run a function on a different CPU. So for example, I can have a non-pure function here called foo, and just see out hello world, not pure. Okay. And so if I ran it right now, what is this going to print? What is that going to print at the screen? Calling foo. I'm fuzzy. I'm fuzzy. Come on, camera. Go. You can do it. You can do it. No. It's going to print out hello world and test pass, right? Now, what if we want to run this on a different CPU? We could do this. Thread t foo. And then t.join. So this is going to run the function foo on a different CPU. It might actually be on the same CPU as us. We don't know. It's up to the thread scheduler to decide where it's going to run. But I can do something like this and run it on YY 9P. And too many. Oh. Let's do this. Keep. So this is going to run the foo function on 10 different CPUs. Okay. And then it's going to wait for all 10 of them to finish. If you don't wait for them, main will continue running, and main might very well actually quit while those threads are still running. You'll get a seg fault. So this is the syntax. This is learning point number 1 for today. I guess actually learning point number 1 is this. pure functions are nice. A pure function is something that has no side effects. Try to use them as much as you can. Don't try to put cins and couts inside of functions. Now, you can see out something like when you're debugging or something like that, but like don't actually have any code as much as you can that manipulates global state inside of your functions. So here we have learning point number 2. Number 2. This is how you can run a function on a different CPU. And we could actually say cout main is still doing main things. And we can even wrap this in a for loop. For I equals 0, I is less than, I don't know, 100, plus plus. So what's going to happen is that these 10 function calls are going to get run on 10 different CPUs. Now, we only have 4 CPUs on the server, so it's going to schedule them however it sees fit, whatever CPUs have the most, available resources on them, we'll probably pick them up. But in the meantime, we're going to be doing our things. And as I said, this ties in a lot to networking. Now, the networking you have to do for Battle Shipperty or Jet Volley Shipperty is very simple. It's blocking the client sends something to the server waits for it, it sends something back to the client waits for it, sends something back, ba-bum, ba-bum, ba-bum. In real life, what you do at small to medium scales is you spawn a thread, and each thread will talk to its own client. So when you accept a new connection as the server, you spawn a thread off, and that thread will be a copy of the server for that client. So the client sends in data, you respond, and every client gets its own copy of the server, essentially, that it talks to. Like a web server or something like that. Hey, give me this page. Okay, here you go. Hey, give me this. Okay, here you go. And each client has its own copy of the server that is like fielding requests for it. So when you do a thread, though, learning point number 3, when you use threads, you have to either join or detach them or crash. Okay. So joining means it blocks. It waits for the thread to finish. Detach means go and do your own thing. I don't care about you anymore. Okay. And so if we detach thread 1, then T can do its own thing. We won't wait for them. Okay. How can you use shared resources? You need to protect shared resources using mutexes, basically. So if you have a global variable like we had up here, you need to create a mutex that will protect it. And so only one person can read or write to that variable at a time. Right here, though, we're going to have some fun. Okay. So we've got 10 different threads. They're going to be spawned off on 10 different CPUs. They're all going to be printing out hello world as much as they can. Main is going to be printing. Main is still doing main things 100 times. And, well, let's see what happens. So you can see we have hello world. We got like 8 hello worlds. Then we have like 100 main is doing main things. And then we have 2 hello worlds. And then test backs. We run it again. We see when every time we run it, different things can happen, right? When do the threads run? Who knows? Nobody knows. When do the threads run? It's up to the thread scheduler. So every time you run this, you get different outputs, right? Like where the, here they all happen at the beginning. This one had 4 at the end. Do you guys understand? So we can run code on different CPUs. Might even be our CPU. We don't know. Could be any one of the 4 on the server. You guys have any questions about this? Ask a question. Let me put it that way. I know you have questions about it. Ask a question about it. I want to see everybody online right now. Hazelton, YouTube. There's a couple pretty obvious questions here. For example, well, Ask your questions first. Can it make me grilled cheese? That's interesting. I almost had a grilled cheese. I ended up getting ham and Swiss, though, instead. What if you need to worry about syncing an action, or do you if you need to do it in a specific order? Synchronizing between threads, yeah, it's kind of a thing, right? Like you're telling it to kind of run at its own pace, right? And so join is kind of what you do, right? You block and wait for it to do something. It's a good question. What about if I want to run sum up here? How do I call this bad boy? Is this multi-threading? It is most definitely multi-threading. Okay. So I'm calling sum up here, but sum up takes 2 parameters. How do I pass those parameters to sum up? It's actually kind of weird. Okay. Another parentheses. Nope. This will actually not work because now you're calling sum up, and the result of that is going to be passed to the constructor of the thread. What you have to do is this. So you actually pass to the thread constructor the name of the function. You pass a function pointer in, and then you pass the two parameters here. So if we pass in 0 and 100 here, it's going to add up all of the values from 0 to 100. But wait a second, how do we get the return value out of it, right? Because it's running on its own. Join doesn't return anything. So if you want a return value, you use not a thread, you use something called an async. So, but first of all, before we do that, let me show you, like, if we do this vector integers by reference, vector of integers named vec that's equal to 10, 20, 30. And so we'll do all that, and then we'll say for every integer in vec sum plus equals x. So we're going to add up all the numbers from x to y, and we're going to add up all the numbers in vec, and we're going to pass it in by const reference. It is no longer pure exactly because somebody else could be modifying this, possibly. But we're going to add up all the numbers from x to y, we're going to add up all the numbers in vec, and return the sum. So how do we pass this in here? All right. So we pass vec here. Vec is now 60 higher, so it's 1. Yep. So this let's see here. So we can give that a break. There we go. Yeah, const reference is fine. Const reference, it works fine. But if you're passing something by reference to a thread, you have to use this weird thing here. This is a standard library function that makes basically like a reference object in text. And so if you want to pass an object to the thread by reference, then you use the reference, stood reference call. And then that's how you kind of glue the things together. Like I said, it's kind of weird. It's weird. You use commas to separate the parameters, and you use ref, stood ref. You pass in things by reference. Okay. So this line of code here, all right, we're coming to the end of our thread discussion here. This line of code here is going to spawn off to run on a different CPU, or our CPU, who knows. We're going to keep doing our thing. Main's going to keep running. Not very long, because we immediately wait. right? But we could have put any number of stuff in here before we waited for the thread to finish. We spawn off the thing, it runs, it does some computations for a while, and then it returns. We're still not capturing the return value here. We are passing in 0 and 100 for x and y, and vec for here. Notice these things are commas. These are not parentheses. I always forget this. I always just say sum up 0 to 100. No, it doesn't work. Does ref always need the std in front of it? Not at all. Not in the slightest. That works just fine. It is just a to show you that it's a standard library function. Okay, so we're still not getting the return value though, and we can do that like this. We make it auto right val equals async like that. And then we will see out the sum is val dot get. So, learning point number 5. Learning points are coming pretty dense today, in the last day of school. You can use an async when you want to return a value. It returns a future, but who cares? I mean, I care. Maybe I care. I don't know. This is just the easy way of doing it. So it's going to return something called a future. And then on the future, you can just call .get. And that returns this waits basically for the thing to finish. And then once the thing is finished, it returns the return value. So that is essentially the same code that we had as before, except we can return a value from it now. What do you guys think? Pretty easy? And we can have multiple of these. Val 1, YY9P. Let's do one more, I guess. Okay, so this is going to run on 10 different threads. It's going to run the sum up function, and I can make these values much bigger if I wanted. Instead of val 1, we will YY9P. It's possible the optimizer is actually kicking in here. Let's turn off the optimizer. It's still pretty fast. All right, let's make it bigger. 100 million. There we go. Got it thinking about it now. All right. Let's make it a billion, maybe. Now it's thinking. Not finished. Okay. Let's run it. Then you can see over here that all of the cores on the server are now being used, right? You can see it while it was running. HTOP over here was showing all these different threads running. Because there's 10 of them on 4 CPUs, they're not getting 100% of the CPU. they're getting like a fraction of it. But the overall, like if you looked at the overall CPU utilization, is at like 400%, like right there. So my program is running at 400% CPU, and when it finishes, bloop, goes back down. There you go. So that is, and obviously you wouldn't be computing the same sum over and over again. What you'd be doing is passing different values to the different threads so that they could all, be, you got a million tax receipts to process. You give the first 10% to the first one, the second 10% to the next one, the third 10%. You divvy up the work, pass them out. They all crunch the numbers. And then at the end of the day, you can add all the values together, right? So instead of doing this, we could do so we could do sum plus equals ret val1 dot kit. Or you'd use a for loop if I was doing this more practically. So now rather than outputting, all the same number, it's going to sum them all together, and we're going to get an even bigger number or something. Is that correct? Oh yeah, because we multiplied by 10. Right. It's like, it looks just like the previous number. Yeah, there's just an extra 0 here. Yeah, because we multiplied by 10. Okay. So we can hand off to each of the different threads its own chunk of data, and it could sit there and work on it very happily. For example, each one could have its own vector of data that it's like working with and stuff like that. So, in fact, we can even do that. Show you what that would look like. YY9P. So each one of these vectors has its own data. I'm just kind of making up some data here. And then instead of vec here, we'll have like q append 1. Dang it. Q append 2. At Q. Okay. So each one of these threads are now getting their own personal vector that they get to play with. And so now if we sum it all up, we'll probably get some different numbers here. What did I miss? In fact, doesn't exist anymore. Don't need to do it anymore. Okay. And so you can see here that we're getting different numbers now, and they're all adding up all these different things. Okay. So it's not too bad, I think. Like, in practice, in reality, you would have some large data set. Like, let's say you're doing like data science kinds of things, and you've got hundreds of thousands of salary data that you want to process. And so you have a giant vector that has everyone's salary data in it, and you pass that vector by const reference to everybody so it doesn't change and mutate, because again, you want your things to be pure. Right now, they're not pure, right? Because it's actually, we can make this a const reference again. We're not mutating it. So let's stack. So you can pass it by constant reference, and that's pretty safe. It's not entirely pure as long as nobody's modifying the data while the threads are running, it's fine. So I see a lot of people keep thinking about saying something on chat and then just like deleting what they're going to say. So just like say it. It's fine. You guys are like pretty quiet today. Yeah. Yeah, I choose you. All right. So yeah, so basically you'd have like a giant vector filled with like, salary data. The first thread handles the first 10% of it. The next one does the next 10. And you do things like, if you want to find the maximal value, each one of the threads can return what it finds to be the maximal salary. And you can make that quite specific too. Like you can be like, find the maximal salary for somebody who's a senior developer in France, right? And each one of the threads can go through, you have a vector of like a class, like a salary class or something, and you like match based on like country and like position. And then you find the highest salary that matches those criteria, you return it, and then all of these guys get the maxes, and then you max across the return vals. It's called a reduction operation, a reduce operation. Here we're just doing accumulate. So you're taking in all the Vim magic going on. It's not that bad. In the previous class though, like Voss wanted to know how to do that, right? Like how do you indent multiple lines at a time? And that is the double right arrow. So like if you go forward double right arrow, that will indent 4 lines. And if you go like forward double left arrow, that will forward double left arrow unindents this way 4 lines. Kind of useful if you want to time how long this stuff takes, right? You can oftentimes like or you could do like that as well. That also works. So let's see here. Auto start equals clock, and then auto finish equals clock. See out spawning threads took finish minus start microseconds. So you're going to see how long does it take to do 10 threads. It's 491 microseconds. A microsecond's a millionth of a second. So it's not too bad. And then if you want to find out how long it takes to do the actual stuff, say start equals clock again. And finish equals clock again. And what I was going to say is you can like do something like that. It's like you can see where's the start, where's the finish, and just kick it over. Kind of looks nice. I don't know. You can do visual mode. Visual mode is V, double right arrow, and indent it that way. That's another way you can do it. Can I multi-thread a process that uses the same resource? You have to be very careful. If people are hitting the same data structure, then you're not pure, right? The point of today's lecture actually is the beauty of pure functions, right? Pure functions can be multi-threaded very easily. If they're all accessing the same resource, like you're trying to do topological sort or something like that, then and you're manipulating and reading, and you have to use a sym4 or a mutex. So if you wanted to mess with global or something like that, then there's a couple different ways you can do it. You use atomic functions. You can do atomic adds, and that's safe. But in general, what you want to look up is this. And there's like lock guards and things like that. Helpful. Not helpful. There we go. Okay, so here we have a global, right? And then you create a mutex. And then what happens is when anybody's going to be, here you have multiple threads manipulating this value up here. You lock the mutex. That gives you only one thread can have that mutex locked at a time. And so if you have 10 threads and all of them try to grab the lock, whichever one grabs it first has it. And then then everybody else blocks. Everybody else waits. And so that one person who grabbed the lock can now do whatever kind of manipulations on the graph or globals or whatever shared resource you have. And then when you're done with it, you got to make sure to unlock it. Otherwise, you're going to be in dire straits. So you do a lock, you do whatever it is you need on the shared resource, like a file, network connection, whatever. You lock it, you do your stuff, you unlock it. And then of the remaining, 9 people, they all jump for the thing and one of them gets it. And then everybody else blocks, they freeze. And then that person does their stuff and then releases it. Then the other 8 jump on it. And so basically threads will sit there and you don't get very good performance out of it, right? Because, all of your threads are just sitting there like, okay, well, I guess I'm waiting for this locked. So in general, when you do multi-threading, the best applications are those where each person is given its own chunk of data to work on, and it doesn't have to be it would be bad if I don't know, you had a queue and each person is pulling data out of the queue to do the arithmetic, because you could only have one thread pulling from the queue at a time. So you'd have to lock it, pull the data, then unlock it. And so everybody's would be constantly blocking on acquiring that lock. It's much better to set up your data in such a way that each person is just given, like what we have over here, each person is just given their own chunk of data. I just made up some data here, but each one's got its own vector. They're not interacting with the other person's vectors at all. That's why I made them separate vectors. They each got their own vector. There's no possibility for a person to push back and then trigger a reallocate, which would hose everybody else on it. They're each given their own private variables. So mutexes are the way of protecting shared resources. Now somebody could just ignore the mutex and just modify it. Main could just change it if they wanted, but as long as everybody's respecting the mutex. Typically, you'll put this into a class or something like that, or you can use a lock guard, which is a little bit nicer. So the lock guard automatically locks and unlocks for you. So when you construct the lock guard, it tries to acquire the lock, and if it does, it continues on. And if it doesn't, look at that code, Hazelton. Yes. While iterations goes towards 0. Somebody used it. I love it. So one person will grab the lock, and then when they return, they release the lock and the destructor. So the lock guard is typically a little bit better than using a manual lock and unlock thing, because you can't forget to unlock when. So we can just be processing all of our data on all these different threads, grab the return values, and then have main, do some final processing or something like that. This is a perfectly acceptable way of doing coding. And so that is multi-threading, my friends. So any questions? There's many different ways of doing parallel processing. OpenMP, which never seems to work very well for me. I have a prettier setup to format everything for me on save now. Makes sense. At what point are you expected to be able to do this? I think you can do this right now, right? Just you call async, pass it the function name, pass the parameters to the function, and then it runs the function on a different CPU. That's it. There's just this little bit of annoyingness where it's well, are you done? You are? Okay, great. Give me the return value. If you're not done, it just waits for it to be done. So there's a little bit of you're go do your thing, and then you sit there and wait for it to be done. And that's it. If you know how to do a function call, you could you could do an asynchronous function call. I would say 41 for this, for async. If you're going to be writing a Battleship server that supports multiple clients, then you would spawn off a thread for each person that connected. The more complicated parallel processing things with like mutexes, and the reason why I didn't really go very deep in that is because I mean, it's not too, like a lock guard's actually not that bad to do, but it's like junior level. You know, I took 2 different parallel processing classes when I was a junior, and decided to make it my specialty. So this is like my my jam, so to speak. High performance computing. Getting to play with supercomputers is pretty fun. San Diego has the San Diego Supercomputing Center, which is full of very expensive machines that you can make them print Hello World faster than any other computer can print Hello World. Kidding. And not all schools do have upper division parallel processing classes, but this is a pretty good, like, I feel like the C++ people have actually done a pretty good job making it pretty easy to run a function on a different, CPU. The only tricky part, like I said, is how you pass in parameters is a little bit weird. And when you do call by reference, you have to pass ref around it. That's about it. That's about all I can think of. You can time it, I guess. So let's see here. And are we not printing the time? Yes, we're not printing the time. So it took 3.2 seconds. If we want, we can convert this to seconds. Or you can use Chrono. Chrono is the C++ way of doing timings. Chrono is also extremely verbose, so I'm not really a huge fan of it. Just because it makes your code look kind of... I mean, I use it. I do. Like, there's just a certain amount of beauty to just being able to, like, give me the current time in microseconds. Give me the current time in microseconds. And subtract them. Like, there's nothing simpler than that. And I like simple code. I'm a simple guy who likes simple things. Chrono is annoying. Yeah, it just you have lines of code that are like this long, and they're like, yes, that's how you should be coding with where you have to like scroll to the right on the screen. Just buy a wider monitor. What's the problem? Just buy one of those quad ultra wides that wrap around your desk. Then you can see your lines of code in Chrono. Yeah, so let's see what happens if we 3.2 seconds. Okay. So let's just pop off like 8 of them. So you notice that it wasn't a linear time relationship, right? So each of these threads took 0.3 seconds to run, amortized. And each of these took no, actually, it's actually exactly the same. Interesting. Yeah. We shouldn't be able to get full throughput on 10 threads, right? Because we only have 4 CPUs. The server itself is not a great platform for testing parallel processing on, because it's a virtualized server, and I don't think the thread manager works properly on it. But at least you can see on HTOP it is trying to move it to different CPUs and things like that. Yeah, exactly. Let's put some Chrono up in here. All right, let's do this. All right. std chrono steady clock time point time start equals std chrono steady clock now. Great. And then let's do that again for the finish. Time finish. Now we need to have a duration cast. CPU reference chrono duration cast. And now duration cast. There we go. All right. Copy and paste from CPP reference. Oh my gosh, that's ridiculous. Okay, so int in milliseconds. Now give us seconds. Chrono seconds, and we'll do time finished minus time start. Let's make it a microsecond. Yeah. All right, it has dot to, what is it, count? Yeah. See what I mean about chrono? It's just like, it's better, but man, is it not easy to type. Let's try here, microseconds. Call this US instead. Yeah, interesting. These guys do not agree with each other. Huh. It's wild. 0.3 seconds for chrono. And 0.6 seconds for clock. Should give us the same answer. Might be wall clock versus CPU clock time. Yeah, interesting. Huh. That's why you create a wrapper for that. Super readable, not excessive at all. Yeah. That's why I create a wrapper for that. It's crazy how much you have to create aliases for. Chrono might be the reason why I start feeling like I'm getting carpal tunnel. Yeah. So, yeah, no, Chrono's better. But man, nothing beats that, for simplicity, right? This is the same as that. Simplicity versus optimization. Yeah, something like that. Elegance of design. Yeah, if you're getting paid hourly, definitely do chrono. If you're in a coding competition and time matters, use clock. Okay, so that brings our discussion of threading to an end. You guys should be able to spawn off a thread to run on a different CPU and pass things by reference to it and get return values from it using async. So did I go over async threading? It's right here, dude. Right, it's right there. And did I go over it? Yeah, you just call async. You pass in the function name, the parameters, and then later on you call get and grab the return value out of it. That's it. It's very easy to use. Okay, so that brings the semester to an end. I will now hang out for the next half hour helping you guys with your projects. Thank you all.